Comes on everyone, let's start off. The last thing that we did was the meta bridge. We did do some introduction on it. Others do keep your cams on. Okay, great. No. So when you use this meta bridge, right? So the idea is pretty straightforward. It is based on the Wheatstone bridge, right? You should know how the picture looks there. So there are certain precautions you have to take while you're doing an experiment with this. Precautions. The first thing is called end corrections. So when you're tying that, resistance wire, it is not like you can exactly put the length of the wire. You need some, wire to connect it. So some length. So since some length is used to connect the wire, right? So that leads to, we need to include them. So exam they'll give you like this. So this is your unknown resistance, Rx. This is R. I'm just putting a simple thing here. So this is the jockey there, and this is what they will say. They will say the right end correction is 1 centimeter. Meaning you used an extra wire of 1 centimeter on the right side. Left hand correction 2 centimeters. So you used a 2 centimeter wire on the left side. And now let's say this thing gets balanced at length x and L minus x. So still it is a Wheatstone bridge. So when the bridge is balanced, the current in the galvanometer is 0. Now when you apply the formula, Rx by the length on this side will be R naught by L into this length would be x plus 2, because the left hand side it is not x anymore, it is x plus 2. And the right hand side it is R by R naught by L into L minus x plus 1. Get in the difference there. So that extra length has to be added. So if this was some 48 and this was some 52, the length is 48 plus 2 and 52 plus 1. Play with this. So this is one end correction. So this is an error that can happen with this. So second thing, the jockey should not be dragged on the wire. Right? Again, the reason is this. Whenever you drag this jockey on the wire, right, there is a chance the wire will become non-uniform. So there will be a wear and tear. So if you just keep dragging it over a span of time, right, the whole wire will get messed up. So you're supposed to lift it and place it at different positions. So lift the jockey, Maybe let's say initially it is at 50, lift it, keep it at 20, lift it, keep it at 25, so and so on. It should be lifted and placed at different positions. The third point, this is the most important one. The bridge must be balanced in the middle 1/3 of the wire. So this actually came in the exam. The question was like this: in a meta bridge, when the jockey is being balanced, in which part of the wire should it be balanced? The first 1/3, the second 1/3, and the last 1/3. So it was like weird. Like, so why does it matter where you balance it? So it has to do with an errors. So let's see that thing. So the bridge must be balanced. In middle 1/3 of the wire to reduce error. So listen to the logic. So this is your Rx, this is your R, and let's say this was X and this was L minus X. Now we already calculated this. So Rx will be R into X by L minus X. Now when you try to find the error for this, how do you find error? Put log on both sides and then differentiate this. So we will get drx by Rx will be dx by X plus d of L minus X by L minus X. Errors are always additive. So this would turn out to be dx by X plus dx by L minus X. So this would be the error in that resistance Rx. Now look at the problem here. If you, for example, let's say this wire gets balanced pretty close to the left end. Matlab X is equal to 2 centimeter, but it gets balanced. Then see what happens here. If X is equal to 2, if the X is very small, this will become big. Suppose if you balance it on the right hand side, that means L minus X will become very small. Then this will become big. You're getting the problem? So that means tomorrow when you do this experiment in the lab, and let's say the length of the wire was 100 centimeter. And if you go and tell the person, right, oh, I got the balancing point at 10 centimeters, he will say, boss, go do the experiment again. Getting it? So that this is again mostly to do with the lab to reduce error. Because if you try to balance it close to the left end or close to the right end, the error will become pretty large. Now, can you change the adjustment? One way to do that is to change this capital R. You change the known resistance. So if you change capital R, you can change that length of X. So you have to keep changing the capital R till you get it somewhere in the middle 1/3. So like I said, this is mostly to do with the error. So if X or L minus X is small, the error becomes big. The best thing that can happen is the midpoint. If your X becomes equal to L minus X, that is X is equal to L by 2, error is minimum. You can get it from maximum minimum. This is another question they can ask you. In a meta bridge, at which point should it be balanced to get a minimum error? But always getting exact midpoint is difficult. So what people say is like, okay, at least in the middle 1/3, right? You get it somewhere. So that's where that statement comes from. Right? So middle 1/3 has less error compared to the left 1/3 or the right 1/3. Because see, theoretically, there is no difference actually. You balance wherever you want, it shouldn't actually matter. But this has to do with errors. Are you getting the logic there? So the midpoint will give you the minimum error. But since you can't exactly find the capital R such that you always get the midpoint, so that much thing is acceptable. This third point is the most important thing. Any doubts on this? So these are the three precautions you should take. The end corrections, the jockey should not be dragged. And the third thing, it should be balanced in the middle one third. So tomorrow when you do the experiment and if you get an answer 90 or if you get an answer 15, you have to repeat the experiment. You have to change this capital Arca value so that the XK value will lie between 33 to 67. Preferably, if it is close to 50, it is better. The closer to 50, the better. So in a lab, they will expect you will get somewhere around 45 to 55 ka beech mein, right? So just give me a minute. Great. So let's see a question on this. So questions are pretty straightforward. They will give you some resistances and all. I'll send you a small sheet on this. So questions are there. But if they do really want to mess up, let's see one question. So in the meter bridge, we took the resistance wire. Let's say this is 3 ohms and this is 4 ohms. You know both the resistances. Let's make it 2 ohms. You kept the galvanometer and we have the jockey here. This resistance wire, you accidentally connected some weird wire here. So this point is x is equal to 0 and this point is x is equal to L. So the resistance of this wire R is given by R naught into 1 plus x by L. So the resistance is changing with x. This R is resistance per unit length. Maybe if R is getting confusing, we can just write lambda. So normally you're supposed to use a uniform resistance, but for some reason you messed up and you connected a non-uniform resistance, but it is still varying linearly. And the bridge is balanced. When the bridge is balanced, this distance was x. Find x. That's it. So whenever you hear the word meta bridge, think of a Wheatstone bridge. Let's see how you do this thing. Root 5L square L minus 2. Right, Samyak. That looks right. Nee, Param, check your answer once. Again, listen to this thing. Even that looks weird. There is nothing there. So indirectly, it is a Wheatstone bridge. So the resistance of this thing. So if I call this resistance as R1, and if I call this thing as resistance R2, because the bridge is balanced, 2 by R1 must be equal to 4 by R2. So we simply get R2 is equal to 2 times R1. And what is R2? R2 is integral. This is the resistance per unit length, which is lambda naught into 1 plus x by L into dx. That is the distance of a small segment. Limits will go from x to L, isn't it? This should be equal to 2 times what is R1? 0 to L. So that is the only difference. The limits will change. 1 plus x by L into dx. Lambda naught will cancel on both the sides. This will become x plus x square by 2L. Limits will go from x to L, and this will be 2 x plus x square by 2L. Limits will go from 0 to L. So this would be L plus L square by 2. So that would be 3L by 2 minus x plus x square by 2L. This would be 2. No, wait, this is 0 to x. 2x plus x square by L. So bring all x to one side, you get a quadratic. This would be 3x square by 2L plus 3x minus 3L by 2. Check, you get a quadratic like this. So you can simplify this further. You end up with x square by 2L plus x minus L by 2. That looks right, I guess. Yeah, looks right. So you can simplify this further, multiply 2L, this will be x square plus 2L x minus L square is equal to 0. Then we get x is equal to minus 2L plus minus root over b square 4L square plus 4L square by 2. This would be L into, that is 8, 2 will go off, root 2 minus 1. Check your answer. Right, Ashita. Right, Utsa. Clear with this? So the main idea is the resistance. And once you got that, it is just a matter of putting the values and finishing it off. The physics got over at this point. Clear. So if you put a variable resistance, the story is still the same. It is still balanced. All clear with this? Next thing. Potentiometer. Now there is something also called post office box based on Wheatstone bridge. We'll see that in the end. Now potentiometer is removed from the mains portion. Right? Last year they did remove from the mains portion. It is there in advance. It is there in boards. It is there in bits. It is there in CET. So I don't know why the hell they removed it. So you still have to do it. So potentiometer. So listen to this carefully. It's not difficult. The most important thing, you should know how the circuit looks. If you know how the circuit looks, after that, it is all about drawing the circuit and solving it. So let's see that then. We will see the whole thing in one go. So first of all, how does this potentiometer look? So what is this potentiometer for? So ammeter measures current, voltmeter measures voltage, meter bridge measures resistance. Potentiometer, it is used to measure EMF of a battery. So all these things which I'm teaching you, right, more than the questions, the theory is also very important. They can ask these as statement questions. It is used to measure the unknown EMF and internal resistance of a battery. If someone just gives you a battery and asks you what is this EMF and internal resistance, we use a potentiometer. So how will the circuit look like? This is your primary circuit. This is your E prime. This is your primary battery. This is your R primary. So these things you know. This here is your potentiometer wire. That is what it is called. It's a potentiometer wire. Resistance is R naught and the length is L. Right? Just give me a minute. Hmm. I don't know why the Amazon people are coming back to back. So this is called primary circuit. Now, for this, we connect that unknown EMF with a galvanometer and a jockey. This is your EX, this is your RX. So EX and RX are unknown. That's what we need to find. Into this, we connect a known resistance, and it is connected here with a switch. So this R is a known resistance. I'll just call it R known. This one is called secondary circuit. There, this picture, you should literally remember this. As long as you remember this whole picture, what is primary circuit, what is secondary circuit, right? You will be able to handle the whole potentiometer you can handle. Now, sometimes in some books, right, actually, if you go to the lab, the picture, if you see, the potentiometer won't look like this. They will use a pretty large potentiometer wire. So this jockey from here, we have the galvanometer, and so that whole black thing is a potentiometer wire. So if you have more length, right? Remember last time I told you, the more length you have, more sensitive you will become. Meaning you can measure even smaller units, you can get more decimals. So the length of the wire is bigger. So this is a long potentiometer wire. So instead of using 1 meter wire, if I use 10 meter wire, I'll get more decimals. This is a long potentiometer wire. Meaning if this was your x was equal to 0 and this would be your x is equal to L, this would be your like x is equal to 0 and this would be your x is equal to, let's say, some 20 L, something like that. You're taking a big wire, 20 times the length. Clear with that? So sometimes you'll see the picture like this. Technically, both are same. This is the picture you need to remember. So just remember, if they give you a big wire here, don't get confused. They're just taking this wire into that. So maybe I'll mark this also in black color. I would strongly recommend. Can you just draw it on your paper? That left circuit, just put it on your paper. Just put EP, RP, EX, RX, RK. That's it. That much symbol. Just draw it on your paper. or else you won't remember and you need this. I'll do one thing. I'll put this in another page. It will be unnecessarily confusing. Okay, let's see. So first thing, we need to find the unknown EMF. So you bring a battery and you want to find the unknown EMF. To find EX. So remember, after you know how the circuit looks, there's only one concept you need to know. So to find EX, we keep the switch open. So open the switch in the secondary circuit and balance the bridge. How do you balance the bridge? Take that jockey and keep on moving on the wire. At some point, the current becomes zero. At that point, you know the bridge is balanced. That is the meaning of balancing the bridge. The current in the galvanometer has to be zero. Let's draw the circuit again. So E prime, R prime. This is your potentiometer wire. So this is EP. This is RP. This is EX. This is RX. This is a galvanometer. It is balanced somewhere here. Since the switch is open, you can remove the bottom part. Let this length be X. Since the bridge is balanced, the current in the galvanometer is zero. If this current is zero, this current is also zero because it is the same branch. Right? Now listen to this thing. This is the most important thing. This point here, if I call this A, this point I'll call it A dash, right? VA is equal to A and A dash will have same potential because they are connected by a wire. A and A dash are same. They both are connected by the same wire. Let this point be C and let this point be C dash. C and C dash are also same because the current in the galvanometer is zero. Because the current in the galvanometer is zero, the potential difference across the galvanometer is zero. That means C and C dash must have same potential. Is that making sense? So this potential difference AC must be equal to this potential difference A dash C dash. So potential difference across AC must be equal to potential difference across A dash C dash. Are you getting why? Because A and A dash are connected by a wire. C and C dash have a galvanometer in the middle, but the current in the galvanometer is zero. So IG, RG, the potential difference is zero. That means C and C dash have same potential. Therefore, AC ka potential difference is equal to A dash C dash ka potential difference. Is that clear, everyone? Understood this point? Please ask me if you're confused because this is the whole crux. If you got this, question is over. That's it. These are the only two things you need to solve potentiometer circuit. How does the circuit look like? And whenever the bridge is balanced, AC ka potential difference is equal to A dash C dash ka potential difference. These are the only two concepts. All clear with this? And once you're done with this, the current in the primary circuit is capital I. Capital I. This current is still capital I. Current will not go into the secondary circuit because IG is zero. So from here we can find I, which is E prime by R prime plus R naught. R naught is the potentiometer wire ka resistance. And great. So what is VAC? VAC is current into resistance across AC. What is A dash C dash? A dash C dash is nothing but EX minus IG RX, right? But IG is 0, so this term is gone. Capital I is nothing but E prime by R prime plus R naught. RAC is nothing but total resistance by total length into X is equal to EX. Therefore, I get EX is equal to EP R naught by L or R prime plus R naught into L into X. There, you can clearly see, everything here. X is also you measured from the experiment, substitute there, you get the answer. So basically, the potential difference is proportional to X. Are you getting how we did that? C and C dash, right? The potential difference is what? The current in the galvanometer is 0. If the current in the galvanometer is 0, that means potential difference across the galvanometer is 0. That means C and C dash must be same. That's where the difference is 0. Are you clear what we did? That's it. Once you got AC is equal to A dash C dash, you equate them, current into RAC and EX minus RGX, that is the potential difference. You will get EX directly from here. You know EP, you know R naught, you know length, you know RP, you know R naught, you know everything. X will come from the experiment. Substitute there, you get your EX. Just have a look at this thing. So you should know your circuit and you should know that AC is equal to A dash C dash. And once you're done, you'll get it. Clear with the steps? Now in the lab, this is not how we do the experiment, but this is the idea there. So from here, we get EX is proportional to X. So that means the more length is balanced, the more the EMF of the unknown battery. Now, the reason why we don't use this directly in the lab is because every time you have to measure EP ka value, R naught ka value, length of the wire, RP and R naught, there is no guarantee these values will remain same. Maybe the battery which you're using, maybe its potential is decreasing. Maybe it is getting spoiled. So it always creates an issue. All clear with this page? So let me show you how they'll actually do it in the lab. But this is the theory behind a potentiometer for finding EX. Clear? Now, what you do in the lab is this. We bring two cells, one unknown and one known. We use two cells. This thing came in example of EMF E1. This is our unknown value which you want to find. And E2, this is the known one which you already know. You bring that. We repeat the experiment. By keeping the cells in same polarity and reverse polarity. So first you keep them in same polarity, measure the balancing length, and then reverse polarity, find the balancing length. I'll show you how it looks. And let the balancing lengths be L1 and L2. Again, draw the picture. E prime, R prime. So you keep the batteries in same polarity. You keep the batteries in reverse polarity. E1, E2, E1, E2. Plus, minus, and let this length be L1. Plus, minus, plus, let this length be L2. Now, just now we proved that the EMF is proportional to X. That means when they're in the same polarity, E1 plus E2 is proportional to L1. When they're in the opposite polarity, E1 minus E2 is proportional to L2. Since the proportionality constant is same, because see, this is the proportionality constant. EP, R0, L, RP, R0. This is same. This does not depend on the unknown batteries. So I can divide them. E1 plus E2 by E1 minus E2 is L1 by L2. You can simplify it from here and you can get E1 ka value. You can do componendo dividendo, and that would be what? That will be E1. This will be E1 plus E2 minus E2. So this would be E2 and this would be L1 plus L2 by L1 minus L2. There. Now, the best thing about this experiment is, do I care what is the battery, primary circuit ka battery? I don't care. Do I care what is the interruptions of the RP? I don't care. What is R0? We don't know. Length, we don't need. Literally, you can eliminate this EP, R0, L, RP, R0. These values are gone. Because what happens when you bring a new battery, initially it will work really good. But after a few months, the battery might not give 100 volts. It might give only 90 volts. So EP will start going a wrong answer. So before doing an experiment, who will take the headache of going and measuring EP and RP every time? Are you getting this? But in this thing, it doesn't matter what was the value of EP. It'll always get cancelled out. This is how you do the actual experiment. You bring two batteries, one unknown and one known, keep them in series, get the balancing length. Keep them reverse, get the balancing length. The ratio must be same. Is this logic clear? This is how you find the EMF of an unknown battery. And this is the major concept. So what was the concept? When the length gets balanced, when the bridge gets balanced, the potential difference across the potentiometer wire and the potential difference across the battery must be equal, because there is no current in that particular branch. So VAC is equal to VA dash C dash. So current in AC, resistance of AC must be equal to EX minus IG RX. But IG is 0 because bridge is balanced. Once you equate that, you get this relation. This is how you do it theoretically. But in a lab, we have a problem. Measuring EP, RP is not that easy. Every time you'll get errors. So a better idea would be bring one more battery, which value you already know, put them in series, put them in parallel, and finish it off. Meaning put them in series in reverse polarity and same polarity. Get two readings and get it done. Is this clear, everyone? This is the theory. This is the equation. So exam the question was given something like this. There was an unknown battery and there was a known battery of 10 volts. When they're in the same polarity, balancing length was 60 centimeters. When they're in reverse polarity, balancing length was 40 centimeters. Find the EMF on unknown battery. Bas itna hi question tha. Straightforward. People who knew the experiment, what they're talking about, they got this in less than a minute. People who didn't understand same polarity, reverse polarity, potentiometer, balancing length, all these are like little weird. So they had a problem. Okay with this? So there, you found the EMF of the battery. Next thing, you want to find the internal resistance of the battery. To find Rx, don't worry, we will do few problems. That should take care of it. And also send you a sheet on this thing. On all these instruments, I'll send you a sheet of 25, 30 questions. So we already did half of them, so that should take care of it. Now to find Rx, what we do, we close the switch. Why should we close the switch? Simple reason. As long as this switch is open, there will be no current in the no current in Rx. If the current is not flowing in Rx, I cannot get it in an equation, isn't it? Every time if Ig into Rx becomes zero, how will I get Rx from there? So we need to let the current flow in Rx. So close the switch and again balance the bridge. So that switch was the thing there. So by opening and closing the switch, the circuit changes. Again, draw the new circuit. E prime, R prime, EX, Rx. This is R known. Story is the same. When the bridge gets balanced, the current in the galvanometer is zero. Now see, if this current is zero, this current has to be zero. Any idea why? See, let's say if the current is I, and if you say current I is flowing here, then this current will be I minus I. And here, if this current is zero, that means this current is I minus I. So this is I minus I. So you're getting I minus I. So battery is giving capital I, but you're getting back only I minus small I, isn't it? Do you guys remember that? I taught you one thing. If you take two circuits and connect them with a single wire, there'll be no current in that branch. You always need a way to go and a way to come back. So here, if you say Ig is zero, that means there is no way you can, that means no current is going back to the primary circuit. So you cannot have any current in this branch also. This is the first point. Is this clear? If Ig is zero, the current in this guy also has to be zero. Because if the current goes into this circuit, there is no way this current will go back to the primary circuit again. All clear with that? That's your first point. That means the upper circuit and the lower circuit are behaving independently. The upper circuit doesn't care what the primary one is doing. So let this current be capital I, capital I, capital I, and capital I. And the current in the secondary circuit be small I, and small I. Both the currents are just rotating, randomly on their own. So capital I is nothing but EP by RP plus R naught. R naught is the resistance of this, and small I is simply EX by RX plus R. Now, since the bridge is balanced, this point is potential A. This point is also A. I'll call it A dash, and this is also A dash. If this is C, this is C dash. This is also C dash. Again, same logic. That means potential across AC must be equal to potential across A dash, C dash. Why? This whole thing is the same wire. So all the points have same potential. This point and this point have same potential because galvanometer ka current is zero. And these two are connected by a wire. So this point is also C dash. Is this statement clear? So potential difference across AC must be equal to potential difference across this resistor must be equal to potential difference across this battery. All those three are in parallel. They should have same potential difference. Anyone has a doubt on that statement, please ask. That AC will be equal. So this AC must be equal to this, must be equal to this. That means capital I into resistance across AC must be equal to small I into R must be also equal to EX minus I into RX. So you can write all three of them, but I'll just use these two. So capital I will be EP by RP plus R naught. RAC is total resistance by total length into X, where X is your balancing length. So let's say that is where you got balanced. Small I is EX by RX plus R into R. Now, if you notice this, if you rearrange all the terms, you end up with Rx plus R will be Ex, which you know already, you calculated this, into R, into L, Rp plus R naught by EP R naught X minus R. There. You know everything here. You know Ex, you know R, you know L, you know Rp, you know X ka value, you know minus R, you know everything. And this is how you find the internal resistance. If you look at this equation here, except Rx, everything you know. Again, what did we do? Same story. First, you should know how the circuit looks. Second thing, VAC is equal to VA dash C dash. These are the 2 points. So you want to find EX, open the switch. You want to find RX, close the switch. Any doubts on this part? Again, but in the lab, we don't do this. This is the theory behind it. Lab may, again, like I said, you really don't want to bring that EP into picture. The primary battery, right? If you just leave the battery there, after 2 months, the battery ka EMF will change. So every time you do the experiment, no one wants to go and check EP ka value kitna hai, what is RP ka value, is the potentiometer wire is good. It's pretty risky and takes too much time. All clear with the story here? So what they do in the experiment is this. They'll put the battery, they keep the switch open. When switch is open, the EMF will be only EX because there is no RG. Let the balancing length be L1. Then we close the switch. Let the balancing length be L2. But when you close the switch, there will be current in the battery. That will be EX minus I into RX. This is proportional to L2. And we also know I is nothing but EX by RX, unknown resistance, plus R known. The proportionality constant is same. So E by EX minus IRX is equal to L1 by L2. We eliminated EP from here. Take this I and substitute here. And the best part, we don't even need EX also. So EX minus EX, so I into RX will be EX into RX by RX plus capital R. L1 by L2. EX will cancel everywhere. We get RX plus R by R is L1 by L2. So from here we get R is equal to L1 minus L2 by L2 into R, where R is that known resistance. So capital R is this guy. You're getting this? So in this, if you see, right, I don't care about EX, I don't care about EP, I don't care about RP, I don't care about R naught. You will get the answer in terms of L1 and L2, where L1 and L2 are the balancing lengths when the switch is open and when switches is closed. These are balancing lengths. So at this length, that AC becomes equal to A dash C dash. This is how you actually do the experiment. So this is how you get it theoretically, and this is how you get the experiment. Clear with this? Because what is the potential difference? This is the potential difference. No? You could have taken I into R also. Matlab, you could have said this is proportional to I into capital R. That also would have worked actually. That would have been faster, I guess. I'll do that only. Wait. I into R. So this is basically your AC. EX by EX into R. There, you get it in one step there. So this is also fine. Clear what we did? So the idea was this: when the switch was open, this length, it depends on EX. When the switch was closed, this potential difference will depend on this distance. which was L1 and L2. Clear with this? The primary circuit will think the EMF of the battery is EX minus IX or I into R. So both are same. So I'll write both if you want. E into IRX is equal to I into R. This is proportional to L2. So both are same. All clear with this? You should definitely, after the class gets over today or tomorrow, sit and, I don't say don't read through it. I would say derive it again on your own. This is important because even if you're in HSC or CBSE boards, this is a 4 marks board ka question. They'll ask you, draw the diagram of potentiometer and explain its working. You literally have to tell all this story there. It is also there in your lab. It is also there for advanced paragraph. These are really good questions. So that's what I'm saying. This thing is there everywhere, and for some reason, these people removed it in Mints. So clear with this? This is how you find EX and RX. Open the switch, you will get EX. Close the switch, you will get RX. It's still not over. The precautions are the most important ones. Now, when you do this experiment, you have to take certain precautions. The first precaution, the primary battery ka EMF must be greater than the unknown battery ka EMF. We will not know this until we do the experiment. Why? Let's take an example. For simplicity, I will not take any internal resistance for the battery. So let's say this is your primary. Now, let's say you accidentally connected a low volt battery. Let's say EP is 20 volt. And let's say your EX was 30 volt. Now see what would happen. Let this point be 0. So we'll assume 0 potential here. You can take 0 anywhere. If that is 0, this becomes 20. If that is 20, this is 20, and this is 0. Agreed? Now, if this is 20, this is also 20. And what is this battery here? This is 30. That means the negative terminal will be minus 10. Do you guys agree with that term? Now you tell me on this potentiometer wire, if this is 20, you'll get 15 somewhere here, you will get 10 somewhere here, you'll get 5 somewhere here, you'll get 0 somewhere there. Will you get minus 10 anywhere on the bridge? You will not get minus 10 anywhere on the bridge. And if you can't find minus 10 anywhere on the bridge, that means the potential difference across the galvanometer will never be 0. That means no matter how much you move this jockey, you will never get IG 0. We cannot find minus 10 on the bridge. On the bridge or the potentiometer wire. Therefore, IG will never become 0. And if IG is never 0, you can't solve the problem because the whole story was based on that IG is 0. Are you clear what happens? The experiment will fail. No matter how much you move the jockey, you will not find a point where IG becomes 0. And then you understand like, oh, something went wrong. So then maybe you change the battery to a higher voltage or something. Clear with this? This is the first precaution. The primary battery ka EMF must be greater than the unknown battery. Accidentally, if you connect a lower battery, it doesn't work. Any doubts on precaution 1? Precaution 2. The primary battery and the unknown battery EX must be connected in same polarity. Now, if you see the picture that we drew, maybe you didn't realize, but this was plus, this was minus, this was plus, and this was minus. I kept both the plus terminals together and the negative terminals on the other side. But let's say in the lab experiment, you forgot and you accidentally connected it in reverse. Again, let's draw the picture. Again, I'm not taking RP just for convenience. You connected in reverse. So this is plus, this is minus, this is minus, and this is plus. Let's say E primary is 100 volt. Ex is 10 volt. So you took a small battery. Condition 1 is satisfied. EP is greater than Ex. But now see what happens. Let this point be 0. This point will be 100. If that is 100, this is 100. This is 0. This point is also 100. But if this is 100, this point will be 110. Understood what happened? If that is 110, on the bridge, if you see, if this is 100, this will be like 80, this would be like 60, this would be like 40, and this would be like 20. So you will have 0 to 100 on the bridge, and you got 110 here. You will not find 110 on the bridge. So even though EP is greater than EX, this will fail. Again, IG won't be 0. If IG is not 0, you can't solve the equations which we did. All clear with this? This is the second precaution that you should take. They should be in same polarity. The third one, the important one, meaning most people, I have seen this thing, right, coming in advanced many grand tests also for other institutes also. They didn't ask before, but it could be a statement question. The third precaution, that R naught, the potentiometer resistance must be much, much greater than internal resistance of the primary circuit. This RP is your internal resistance of the primary battery. So what happens? Again, example, let's say the primary battery, this time I'm taking RP. So let's say this is 100 volt. Okay, and let's say this is a 60 volt. They're in same polarity. So condition 1 satisfied, EP is greater than EX. Condition 2 satisfied, same polarity. But let's say your R prime is 50 ohms. And let's say your R naught is also 50 ohms. So accidentally they both became equal, or maybe RP became really big. Now see what happens. If you take this point as 0, this point will be 100, this point will be 100, and this point will be 50, because if this is 50 ohms and this is 50 ohms, they will divide the voltage equally, right? You'll get 50 and you'll get 50. If this is 50, that means somewhere here you'll get 40, somewhere here you'll get 30, somewhere here you'll get, 60, you'll get 90, 80, 70, and 60. Now, if this is 100, this is also 100. If this is 60, this will be 40. Will you find 40 anywhere? So what actually happened is, even though you're using 100 volt battery, because both the resistances are equal, this will take 50 volts, this will take 50 volts. Make sense? So this wire here is behaving like a battery of 50 volts now. You got the catch? Even though the battery had 100, because of that internal resistance, you lost half the voltage in the battery only. What you got outside was only 50 volts. So this thing was acting like a 50 volt battery. So when you kept a 60 volt battery, it didn't get balanced. Are you getting the reason? For example, let's say if this is 1 ohm and this is 99 ohms, then what would happen? This will get 1 volt and this will get 99 volts. That means this wire will act like a 99 volt battery. Are you clear the catch? That's why if R naught is much, much bigger than RP, most of the battery ka EMF will come across the potentiometer wire. Are you clear? So that RP is like hidden, like, one of the neglected thing. People don't realize that RP can mess up the whole thing. Suppose, let's say your RP was 99 ohms and the R naught is 1 ohm. Then what would happen? 99 volt will be eaten by the internal battery. This wire will act like 1 volt battery, isn't it? What will you think? अरे मैंने 100 volt battery use कर रहा हूँ. So you'll bring 10 volt battery to balance. It won't work. Are you clear with the reasoning there? This is your third precaution. So potential difference across RP and R naught will be 50 volt each. Because here they're equal. So therefore, the potentiometer wire is behaving like a battery of 50 volts. Therefore, IG will never be 0 because this battery is 60 volts. Clear with this? So by taking RP, by taking R naught much greater than RP, maximum voltage will be across the wire. So these are the three cases where the experiment can fail. The first one, EP must be greater than EX. Second thing, they should be in same polarity. Third thing, RP must be very small. This is the whole thing about the potentiometer. First thing, you should know how the circuit looks. Primary circuit, secondary circuit with a switch. Second thing, to find EX, open the switch. Current will not flow in the galvanometer. That's why we say bridge is balanced. And the idea is the potential difference across AC must be equal to potential difference across A dash C dash. Why? Because A and A dash are connected by a wire. C and C dash, there is a galvanometer in the middle, but there is no current. Therefore, there is no potential difference. So A and A dash ka potential is same. C and C dash ka potential is same. Therefore, voltage across AC is equal to voltage across A dash C dash. Once you got this, you can find the current in the primary circuit, which is E prime by R prime plus R naught. That is your capital I. You can find the resistance RAC, which is R naught by L into X, where X is the balancing length. We get EX. This is how you get it theoretically. But this is a bad idea when you do an experiment because that EP ka value and RP ka value can change with time. So what we do, we bring two batteries, one known and one unknown, E1 and E2. Put them in series, same polarity, reverse polarity. You get two balancing lengths, L1 and L2. Proportionality constant is same. Divide them, we get E1. This is safer because you need not worry about what is EP ka value and R naught ka value and RP ka value. This is how you do unknown battery ka EMF. If you want to find the internal resistance, you have to close the switch. Once you close the switch, the current will flow in the primary circuit, the current will flow in the secondary circuit independently. The currents will not interfere with each other. We get two currents. Again, the story is same. Potential across AC is equal to potential across A dash, C dash. Equate them, you'll get RX. This also, again, we don't like because same reason, we don't want to deal with the DP and RP. So what we do when we keep the switch open, we'll see what is the balancing length. When the switch is open, the potential difference across the battery is EX only because IG is 0, right? When switch is closed, potential difference is EX minus IRX or IR is equal to L2. Equate them, you'll get your RX. Then you have to take three precautions. EP must be greater than EX. EP and DX must be in same polarity. And the third one is R naught is greater than RP. That's your whole story. Clear with this? Take a break. Come back after that. We'll start doing some problems on this. That should make things more clear. Come back by 9:45. We'll continue from here. Any doubts in the theory? Anything you're not clear, please ask. But best thing, we'll do 3-4 problems. You'll get the hang of it. Chalo, come back by 9:45 then. Yeah, let's start off. Great. So, So how does this potentiometer actually look like? Even though the big whole setup I showed you, in reality, it would look something like this. This would be the size of your thumb. Look at this picture. This is the internal construction there. So what is happening is this. I'll name the alphabets here. So this one is there. Look at this thing. This ring is there. This is the potentiometer wire. This wiper is there. This is that jockey, which is moving on. So if you look at the points here, this is point one. This is point one. This is point three. Use another color. So this is point three. This is point one, and this is point two. So you're connecting the battery between one and two, right? And the galvanometer is connected between one and three, and the galvanometer is connected between two. So now when you move this thing, so the jockey is moving on this wiper. And how do you move that wiper? You can see the thing on the top. You can rotate this. This screw kind of thing can be rotated. So when you rotate this, the wiper rotates. Moves the wiper. So here, wiper is the jockey. And this circular resistor track is your potentiometer wire. So this is a very small potentiometer, works really good. So you can adjust the things from here. So this will be the size of your thumb. It is so small. This is the practical one. No one will actually carry that big, the size of your hand and put it in a lab and do that. That's, yeah, to show it looks good, but this is the practical one. Now, let's see some questions on this. That if you got the first one, you actually understood the whole potentiometer story. So let's get this. Two parts to the question. Uh, there's one new word called rheostat. So rheostat is nothing but a variable resistance. So if you say 10 ohms, this is the symbol for a rheostat. That means by moving that jockey, you can change the resistance of the thing. So this is one more new term there, rheostat. So in the primary circuit of a potentiometer, the rheostat can be varied from 0 to 10. So the rheostat is a variable resistance which you can keep going from 0 to 10. Initially, it is at minimum 0. Find the length AP of the wire so that the galvanometer shows 0 deflection. Second thing, rheostat is put at maximum and the switch is closed. So this is the switch. Now it is balanced at 8 meter. Find the internal resistance. Get it? This is the whole story which I taught you. Open the switch, find EX. Close the switch, find RX. Try. Take a minute or two. Think about it. Don't worry if you don't get it. I'll show you. You will get it. Step one, draw the circuit. You know the story. AC is equal to A dash T dash. Okay, let's see the first one. Read the question. Uh, the rheostat is going from 0 to 0. Initially, it is minimum. The switch is open, so I'll just draw the circuit. Say we have a battery, we have 1 ohm. This is the rheostat wire. I'll just put a thick wire there. So this is 10 volt. This is 1 ohm. You're connecting the 4.5 with an internal resistance and the galvanometer. This is 4.5 and this is smaller. There, this is the first part of the circuit. Clear? And now he's saying this thing you want to find the length AP when it is balanced. Great. So if this was A, this was C. I'll call it P here. He took P. Then this will be A dash and this will be P dash. The story is still the same. The distance of this wire was how much? It is 9 ohms and 12 meter. Perfect. That was the picture. So always put a new circuit. Don't be lazy about it. So let's solve this. Step 1, get the circuit. Step 2, since the potential difference must be same, VAP must be equal to VA dash P dash. Because the bridge is balanced, the current in the galvanometer will be 0. So all the current here will flow only in the primary circuit, capital I. So this will be I into resistance of AP. This would be EX minus IRX. So I will be 10 by 1 plus 9 and RAP will be 9 ohm by 12 into X. That is your length AP. IG is anyway 0 and EX will be 4.5. So 10 by 10, that is 1, 4.52. They'll get AP is equal to 6 meters. Is that clear, everyone? All clear what we did? Right, Samyak? Right, Akansha got the first part. Can you get the second part? Now, if you close the switch and the bridge is balanced at 8 meters, find the internal distance of the cell. Let's see. Again, draw the circuit. He's saying the rheostat is put at maximum and the switch is closed. We have the battery, internal distance, the rheostat, the potentiometer wire. Uh, this was 10 volt, 1 ohm. This is 10 ohm. This was 9 ohm, 12 meter. This is connected to this with the known resistance This is your galvanometer, and this is balanced, and this was 8 meter. So this was the whole thing. When the bridge is balanced, the current in the galvanometer is zero. So this current is also zero. So the current is just flowing independently in both of them. This was capital I. And this voltage we already know, 4.5 volt. This is R, which we need to find. And this was 2 ohms. Perfect. Current in this thing will be small I, it is flowing this way. So small I will be 4.5 by R plus 2. Capital I will be 10 by 1 plus 10 plus 9. That is half ampere. Perfect. So this point is A, this point is P, this point is A dash, and this point is P dash. Same story. Voltage across AP must be equal to voltage across A dash, P dash. Right? And then you can equate this. So AP will be I, which is half into resistance across AP. This will be small I into the 2 ohms. So our AP will be 9 by 12, and AP is given 8 meters, and the small I is 4.5 by R plus 2 into 2. 4.5 into 2 is 9. 9 will cancel. 2 there, that is 4, 3. So R plus 2 is equal to 3, and R is equal to 1 ohm. Is that clear, everyone? You have to redraw the circuit and you will see the whole thing. And there are only two things I told you. Draw the circuit and always say the same thing. AP is equal to AP dash. And that's it. You find the current, you do that, and you solve. Any doubts on this thing? All clear with the question? This is that whole experiment. What I taught you, this was the question. Got it? Roughly got an idea what is happening there? Let's see one more. That's the best thing to make things clear. Here is this. Yeah, there's an easier version of that. Okay, option 2 by 3. Let's see. So 6-volt battery of negligible interresistance. So RP is 0. E prime is 6 volt. Of length 1 meter. The positive terminal of another battery is 4 volt. Resistance is 1 ohm. Is joined. Their ammeter shows 0 deflection. AC would be how much? Yeah, you can actually kind of guess and say that means this whole wire is 6 meters, isn't it? If the whole wire is 6 meter for 4 volt, this should be how much wire? 2/3. हो गया ना एक step में. You're getting the logic. The whole wire is 6 volt. You want to get 4 volts. It should be 2/3. But okay, if you don't realize that, let the current be I. Let the current be I. In this current, I is equal to 0. So we don't know the resistance here. So capital I will be 6 by R naught. Same story there. If this is A and this is C, this point will be A dash and this will be C dash. So voltage across AC is equal to voltage across A dash C dash. So this will be I into resistance across AC must be equal to 4 volt. So I will be 6 by R naught. This will be R naught by length, which is 1 meter into the length AC. R naught will cancel. AC is equal to 2 by 3 meters. Yeah, easy. Because the R prime is not there, it is easy to say that directly. All the 6 volts will be across the wire only. Clear? Let's see little more on this. There, let's get these two. So look at that thing. The length of a potentiometer wire of EMF is balanced at length L by 3. If the length of the wire is increased by L by 2, at what distance will the same cell give a balancing point? So what you need to understand is this. So initially, the EMF, the length of the potentiometer wire is L. It is balanced at L by 3. So let's say when the wire ka length was L, right, and you're balancing at L by 3, that means that is an EMF of E prime by 3. So it's understood. So that EMF is E prime by 3. That must be equal to E. Now what you did, you increase the length of the wire to L by 2. So now your total length of the wire is 3L by 2. Now understand, the potential difference across the wire is still EP only. So if you still want to get EP by 3, so to get EP by 3 potential, you need 1/3 of the length. That is 1/3 of 3L by 2, which is L by 2. Is the logic making sense? No matter how big you make the wire, the potential difference across the wire is still E prime only. That will not change. And you said initially it got balanced at L by 3. That means the EMF of the unknown battery is 1/3 of the primary battery. Is that making sense? That means no matter how big the wire you take, you will always balance 1/3 of it. Now, if the new length of the wire is 3L by 2, then the 1/3 of the wire is this. So you can write like this thing. So EX is E prime by 3. Therefore, it always balances 1/3 of the total wire. So if you make the wire bigger, it will be 1/3 of the bigger wire. All clear with that? Bus by logic. There's no need to solve. You can see and figure out few things like this. These are the kind of questions you'll get in bits and mains. 43. In the potentiometer wire AB of length L and this thing, this is also again straightforward. What is the answer for this? Get the second one fast. Right, Utsa. So for the second one, IG is 0. So whatever current is flowing only in this branch, so that capital I will be E by R plus 9R. Voltage across AJ must be equal to voltage across A dash J dash. I'll call this A dash and I'll call this J dash. So that would be I E by 10R. Resistance will be 9R by L. You want to find AJ ka length, so that is AJ. A dash J dash is E by 2. E will cancel. We get AJ is equal to 5L by 9. All clear with this? Hope everyone is understanding what we're doing. If you see repeatedly and doing the same thing, potential across AJ is potential across A dash J dash. That's the game you're playing. Once you figure out that, the rest of the thing is simply you're finding current and doing IR and all that stuff. Any confusion so far? Clear. Let's see a few more. That's it. The best thing is that only you do problems, you will see like, okay, there's really not that different from it. There, this is a little lengthy one. First, look at the picture carefully. Yeah, it थोड़ा weird लग रहा है. Understand one thing. There is no guarantee primary should be always up. It can be up, down, anywhere. So if you have noticed it, this is primary, this is secondary. So be careful. It is reversed. Switch यहाँ पे है. This is 6 and this is your primary and this is the wire. Try. Get this. If you got this, I think then you understood. In the arrangement shown in the figure, when S2 is open, so this is actually the whole thing again. The galvanometer shows no deflection at L by 2. When the switch S2 is closed, the galvanometer shows no deflection at 5 L by 12. The internal resistance of the 6-volt cell and the EMF of the other battery are. So EMF of the other battery is the primary battery EMF is asking. He's asking us, this is something weird. He gave you EX and he's asking E prime. This is what I'm saying. If you should know how the whole thing works, then it is manageable. If you don't understand the working there, then if you just remember the formula, you will have a problem. Let's see. Samyak got it. Harshita got it. Ovia got it. Perfect. So let's see the story. So initially when the switch was open, draw the circuit. That's the story every time. You draw the circuit. Don't be lazy about it. This is your potentiometer wire. This was the battery. This was your galvanometer and this was the thing. So this was 6-volt and this was R and this was E. The jockey was here and your balanced initial at L by 2, you can actually see and guess directly because if L by 2 was 6-volt, then total length must be how much? 12-volt. So then you could have got that step directly without doing anything. But anyway, let's solve. So this current will be I, this current will be I. If I call this is A and I call this E, this will be A dash and this will be C dash. So I'll just write the story again. VAC is equal to VA dash C dash. So this would be I into RAC, and this would be 6. I will be E by the total resistance R naught, and RAC will be R naught by L into AC. AC is nothing but L by 2. A is equal to 6. So then we get E is equal to 12 volt. Perfect. The second thing, you close the switch. So the first part, right, you would have got it without doing so. That would actually save you time in the exam. But I'll just show you because doing it for the first time, so better we do it aram se. The galvanometer is there. So now this we got 12 volt. Same story. So this current will flow in this junction. This IG is 0. This guy will have its own current, small I, in that thing. So small I will be 6 by R plus 10. Capital I is 12 by R naught. This is A. This is A dash. This is C dash, and this is C. Same story. Voltage across AC is equal to voltage across A dash, C dash. So AC ka voltage will be I into RAC. This would be I into that resistance, which is 10 ohms. I into 10. So this will be 12 by R naught, and you're balancing at 5 by 12. So this would be R naught by L and 5L by 12. And small I would be 6 by R plus 10 into 10. I scribbled a lot here. Yeah, you can solve this. R naught will cancel. LL will cancel. 5 to 2, this is 6. 6, 6 will cancel. I got R0, wait. 5L by 12. That's not 10. Perfect. Great. So 12 will cancel. R5 to 12. R is equal to 2 ohms. So B is the option. Clear with this? You could do all this thing, but if you remember, there's a much faster way to do this. We can say, since it is L by 2, the EMF will be this. So then we can say the 6 is proportional to L by 2. For the second part, the EMF, if you remember, I into 10 is proportional to 5L by 12. Yaad hai? This one, the second method which I taught you to find Rx. This method, see? So EX is L1. So he gave you this thing. 6 is proportional to L by 2. EX minus Rx or I into R. So this is I into 10 is proportional to 5L by 12, isn't it? And what is small I? Small I is this. Substitute that, you would have got it much faster without doing all this story. Are you clear? This would save you time if you do it this way. This is how you should actually approach it. But ठीक है, I mean, I wanted to show you the picture and everything and get used to it. All clear with this? Let's see one more, and then we'll go ahead. This I like it. Let's get this. Cams on, everyone. Keep your cams on. Any answers? Right, Samyak. कुछ नहीं करना था. If you actually solve, you'll get an answer 2 meters, which is wrong. Which is wrong. If you actually solve, you'll get 2 meters, which is wrong. That is because you're not looking at it carefully. Look at the terminals of the battery. Plus, minus, minus, plus. They're in reverse polarity. Bridge का भी balance ही नहीं होगा. D is the answer. That's why precautions are important. Questions will come like this. And if you accidentally solve, you'll still get 2 meters because if you take same polarity. So the batteries are in reverse polarity. So this is a precaution too. Bridge will never be balanced. You can't solve this thing. Clear with this? That's the thing there. That's about potentiometer. So I'll send you a sheet. There are 4 or 5 more models. Practice that. That is the best way to do this. It's not tough, but yeah, it's little lengthy and theoretical. तो होना चाहिए, पता होना चाहिए. Next thing, post office box. So post office box is again it's an equipment which measures an unknown resistance using Wheatstone bridge, the same as meter bridge. So why do we call this post office box? Resistance by using Wheatstone bridge. So if you go back some 100 years back, right, when you say post office, now we think about letters and all, but a post office was, the center of technology. During that time, right, all the tech that whatever we have in telecommunication, it is all in the post office. If you ever seen old movies, right, 1970s and 80 movies, there is very one common scene happens in a movie. The hero is there working, and one of his friend come rushing and say, "Hey, you got a telegram, or you got a trunk call." So you got a message from your dad or from your house. Dad serious, father serious, start immediately. That's it. This is the only message, 4 words. Because sending a word is expensive. It used to be very expensive to send a message. The farther the city, the more expensive it used to be. So people, it was so expensive, so people used to use shortest words. Father serious, start immediately. Bas ho gaya. That will tell you everything. And now we talk hours and hours on the phone, we do chatting and all, but it was expensive. Right? Even when I was in school, why in school, even when I was in IIT first year, if you want to make a phone call, it used to be 3 rupees per phone call. It might not look big, but this is in 2006. 20 years back, 3 rupees. Right now, the same 3 rupees would be easily 14 to 15 rupees. Imagine paying 15 rupees to make a phone call for 3 minutes. It was expensive phone calls, right? So during that time, right, people used to use Morse code. You know what's Morse code, right? So Morse code is a very simple thing. So we have a wire and you have some kind of a device there. So with a plug kind of thing. So whenever this needle touches here, the circuit gets completed and the current flows. So you get a sound buzz. When you remove it, it comes off, the sound goes off. Now by continuously tapping this, so when you tap this, you'll get a key, remove this, sound goes off. So if you tap it for long, key, if you tap small, key. So you're getting a dot and a dash. So key, something like that. So if you do a short tap, it is a dot. If you do a long tap, it is a dot. Morse code, 0 and 1 binary. That's the whole point of a Morse code. You're creating binary zeros and ones. So if you actually go and look at the table, you'll find something like this. If you have key, this is A. If you have something like key, this is O. So people have created the whole thing, for that, all the alphabets. This is wrong. You can check out the actual Morse code. You must have seen in movies, na? The hero is being tortured with his eyes. He keeps doing his eyes like this, and the other side, his friend figures out what is the plan, and they come and kill the enemy. Bullshit things. You must have seen this. So it's all Morse code, actually, right? So people actually used to use Morse code during that time for transmission. It might look very complex, but imagine right now we have AI engineers, software engineers like that. During that time, you're a Morse code engineer. So person who knows Morse code, you used to be in a very good job, and yeah, you are like the star of tech. That's a high tech that time. So what these people used to do, right? So telecommunication, right, is actually used for military purposes. It's not for you and everyone to talk. It's all for military purposes, communications. So these people used to establish post offices in every city. Mostly every 50 kilometers, they used to have a post office. So that is how actually they used to fight wars. Imagine, Maharashtra mein there is, Britishers are occupying different cities, and they get a news. Pune mein tomorrow night, a crowd of 3 to 3,000 people are going to attack. Pune mein they have only 500 soldiers. Now, how do you let this information travel very fast? You send a Morse code to Mumbai, Nasik, whatever nearby cities, and tell them, boss, Pune mein attack hone wale, we need reinforcement. So Mumbai say 500 soldiers, Nasik say 1,000 soldiers. So they all gather next day. They're waiting for the enemy to come. So communications are very important. Now what used to happen? Now the enemy also knows, boss, these people are talking in Morse code. So someone used to go and break those wires. They used to break the wires, or maybe the tree fell on a wire, or there is some kind of a problem. So now we have a problem. So we have a post office A, we have a post office B. The distance between them is 50 kilometers. They're both connected by wire by that post and everything. Now accidentally something happened and the wire, right, got broke and it fell on the ground. So we are assuming it fell on the ground. So the wire got disconnected, right? So assume wire is broken and it is on the ground. Now, for simplicity, let's say this thing happened 9 kilometers from the post office A and it happened 41 kilometers from post office B. How do you know the wire got cut? If you open that Morse code ka line, you won't get any sound. It will be blank. You ever seen phone, when you make a phone call, you get that background sound? You get, that means it is working. If the wire is cut, the sound will be gone. So when they open this Morse code, the operator at A, operator at B, both knows, boss, Morse code kaam nahi kar raha hai. So they know the wire got disconnected. Now you tell me who should go and actually repair this? A, right? It is closer to A, 9 kilometers. But how will they know where the wire got cut? So this is what they do. Since we're assuming this wire has fallen on the ground, let the resistance of this wire be X. So here we will take a Wheatstone bridge. We put a galvanometer here. We will put a battery here. And we'll ground this. This is R1, this is R2, this is R3. And this wire which got disconnected, you connected to the Wheatstone bridge. Now, this is also grounded. This is also grounded. So it is as good as connecting both of them. Now, if I just redraw the circuit here, this is how it looks. This is that unknown resistance X. So this is the resistance of the wire which has got cut. So you will change R1, R2, R3 ka values till Ig becomes 0. So once you do that, you will get R1 by R2 is equal to X by R3. From here, you get X ka value. Once we got X ka value, we know resistance is nothing but rho L by area. Rho by the formula, rho is the resistivity, L is the length of the wire, and A is the area of cross section. I know resistivity of copper, I know the area of cross section. From here, I can find length of the wire, AX by rho. So when the sound goes off, both the post offices will do the experiment. A will get a result of some 10, 11 kilometers with an error. B will get an answer of something like 40, 42 kilometers with an error. Now, without even talking to each other, both of them know, right, who has to go and repair. So A will know, boss, it is close to me. So he will take all the equipment and will actually look at the map. Where is 10 kilometers? Is it in a forest area? Is it in some swamp or something? And they'll take the equipment and get it repaired. Clear with this? That's why it is called a post office box. So you can actually figure out where it is done. Now, how will you do this? If you take this R1, R2, R3, right? This is how the setup would look like. So that R1, R2, R3 are actually these plugs here. So whenever you rotate these plugs, pull the plugs, I think you have to pull them or push them. I think you have to push them. When you push them, you get the resistance. So I'll just show you how the picture looks like, say. So this S-shaped thing is there. See how it works. So in the middle, you have these plugs. So for example, let's say this value was 1000, this value was 100, and this value is 10. If this is point A and if this is point B. Now, if you close this plug and if you close this plug, if you just close them, that means this plug and this plug got activated. So the resistance between RAB becomes 1010 ohms. Are you getting it? So by closing the plug, by opening the plug, you can change the resistance. So यहाँ पे ना, there is no need to physically change R1, R2, R3 every time. You can just open the plug, close the plug, open the plug, close the plug, and you can keep doing this till IG becomes 0. It becomes pretty convenient, isn't it? Instead of actually changing the resistance. Are you getting this? So these plugs, right, by pushing the plugs, we can make the resistance active. By pushing the plugs, so the resistance gets connected. So if you push 1000 and 100, you'll get 1100 ohms. If you push 110, you'll get 110 ohms. So you can change the resistance. The resistance is added between the terminals. Then the idea was pretty straightforward. So this is what we do. I'll just show you the circuit here, see carefully. Look at the terminals here. They're already given A, B, C. So we have 3 terminals. D is somewhere here. So if I draw the circuit, where did you keep the unknown resistance? Rx is your unknown resistance. This is connected between C and connected between D. So we have 4 terminals. Where is the battery? Battery is between, you can actually change this key and all, but the battery is actually connected to A. The battery is connected to C. So this is how the circuit looks like. So this is A, this is B, this is C, and this is D. So there are 4 terminals. Between A and B, look at this. Between A and B, there is R1. And so this is R1. Between B and C, there is R2. Between A and D, this is the biggest one. Look at this. A and D, right? You have all these things. The big one in the middle. So basically, they'll mess up with R3 actually. You can change R3 a lot. You can see a symbol here, INF means this is infinity. Means if you plus that plug, the circuit gets disconnected. Infinity means open circuit. Current won't flow through this. And your Rx is between your D and C. So this is where you keep that broken wire. The battery is connected between A and C. And the galvanometer is connected between B and D, obviously. There, I hope you can see the circuit now. Now by moving the plugs, changing the plugs, you will find when the current becomes 0. You know R1, you know R2, you know R3, you can find X. So one important thing here, you can interchange galvanometer and battery and it still works. So you can put the battery between B and D and you can put the galvanometer between A and C. So that is what these 2 keys are doing. You can alternate them. Battery and galvanometer can be interchanged. They do ask questions on this thing. Matlab questions will be straightforward. Between which 2 terminals is the battery connected? between which two terminals, the unknown resistance is connected. They'll ask you those kind of questions. So you can always draw a circuit and you can verify. That is a best way. Galvanometer can be interchanged. This is post office box, which is basically Wheatstone bridge. So don't get too confused about this. And that is the plugs there. Clear, everyone? So that is one main thing there. After that, we are still left out with one or two small things, half deflection method and all that stuff. I think next class we will do that. It'll take another 15-20 minutes. And next class, we will start off with ray optics also, right? So chapter is technically almost done. You can start doing. We're not left with much. Another 10-15 minutes. So okay, we will continue again on next Tuesday from here. We have done almost 45 questions. I'll also send you a sheet on instruments, so make sure to check it out. Okay, with that, we'll wrap up for the day. I'll see you guys again next Tuesday, same time. So any doubts, anything else, stay back. And do remember, there's a test online tomorrow, so make sure to give it. I think it is on